today we'll look at how to derive governing equations, and it's a generalized derivation that many of you might have not have done before. But there is a preliminary aspect that I want to cover beforehand. So before I officially begin the lecture, I need to bring you along with some preliminary example of integral calculus. So what we're going to do is we'll imagine that you are all material points in a continuum, and there are many points, and you're sitting in a cube. Thank you. You're sitting in a cube. So consider this classroom to be a small cube through which you want to estimate flux. Okay, you are sitting in this, and then imagine for simplicity that there is a external field that is coming here. So you can, since this is a small cube, it's not really closed like this, these walls. Let's say heat can come in, heat flux can come in, or if you want to go into heat mass transfer, let's say some moles can come in, and this F is carrying them. And for simplicity, I'm going to assume that this is just unidirectional, fx 0 0. But this fx can be a function of space, meaning that as the flux is coming in, it can come with high velocity in some sense, and the flux could be leaving slowly, meaning that there could be a net buildup of heat. Okay, so it is possible that when you're sitting in this cube and the flux is coming in, you may feel the temperature increasing, okay, over time. So I'm not keeping it as constant, it's a function of space. So I could have written xyz, but we know that we could also write compactly r. And the question is, how much quantity, and that quantity could be anything that you desire, that for the sake of example, heat, mass, moles, whatever. How much Q, let that quantity be Q, is F bringing in, and an emphasis on bringing in, and especially in. This is the question that we are asking. How much of that heat quantity, mass quantity, whatever quantity, is being brought in by this F? And this is the schematic. We're going to assume this to be X, this to be Y, and this to be Z. So how would we find the answer? So flux is what? Whatever quantity you imagined per meter square per second, right? Now that, let's say that this flux, to get the answer, this would be flux time area, and let's say bringing in per unit time. Okay, so to answer this, you could just simply do flux into area, but now we have to be more specific which area we are talking about, right? So let's write more formally. So how many areas do you see? This flux will come and leave predominantly from two areas, because it's only perpendicular to these two areas. The other areas are there, but they won't interact because their surface normal is orthogonal to or perpendicular to whatever is coming. But let's write completely. So there are total 6 surfaces. So let me write down for surface number 1 and 2 and so on. So I could write, so some flux is coming in, and this is Fx, and I'm going to give it a notation 1, meaning at surface 1, because keep in mind that it's a function of space, so it could change with space. So if I'm going to calculate this flux at 6 surfaces, I'm going to denote the flux at each surface location as that 1, 2, 3, 4, 5, 6, and I should multiply it with dA1. What will be 2? Of course, for 2 surface. So let's number the surface. This is surface number 1. Let's say this is surface number 6, surface number 2, and then doesn't matter 3, 4, 5. Okay. So you know that 1 and 6 will only matter. So, yeah. Oh, sorry. Yes, you're right. X. Yeah, X is horizontal. Thank you. Okay. So for 2, what will I write? Fy at 2 dA2. Yes, but it's inconsequential because Fy is 0. There's no y component. And I could write for 3, 4, 5. I will not write and waste your time because it will be 0. So from 2 to 5, it will all be 0. Yes, time to time I'll do the treatment for 2 also so that you know what's happening. But what's important is 1 and 6. 6. Fx at 6, dA at 6. But through this area, F is leaving or not? So the question was how much flux is coming in or how much quantity that flux is bringing in. So this has to be treated with a positive sign because this brought in, and this has to be treated with negative sign. Okay, now what I can do is I can write even this more formally as a dot product because I know flux is a vector and also area elements of this cube are also vector, because whenever someone says area and you're speaking about objects, you could say which area out of these 6, which area. Essentially you're telling where is the surface normal of that area, right? Because if you take this area, its surface normal will be pointing in z direction. If you take 1 or 6, it will be in x direction, right? So I could write this this guy as fx, or not x, f1 dotted with ex, the unit vector in x direction, into dA1. Yes or no? Similarly, although it's 0, let's write it because it helps. F2 dot EY dA2. Of course, this is 0 because F has only x component, dotted with y will be 0. And for 6, we can write minus F at 6 EX dA6. And when I write this, what am I doing physically? So this is anyways inconsequential, so I'll focus my energies on 1 and 6. So what I'm saying is that this is my surface of interest for 1 and the rest is not of my interest. Whatever, you can draw a cube if you like. And it is pointing in EX direction and my flux is coming from F direction and I'm taking a dot product. Yes or no? That's what I'm doing. Similarly, I'm doing the same. This thing is not of interest to me. Only this area is of interest. This is pointing in X direction and this is coming in F direction. And I'm taking a dot product of these. Now, we will say, like set a convention which will be true throughout this course, is that since surfaces have a direction or orientation, we will assign them always outward normal. Okay, I'm writing very informally. This English could be here and there. That's fine, but you get the idea. That's most important. So, since surfaces have a direction, we'll assign them always outward normal. Is that the case here? Because it's not. So, we have to change some things. Because see, in here, this surface normal is pointing inward. This surface normal is pointing outward. So, what is our convention? Because see, ultimately, we'll not talk about cubes only. We'll talk about all kinds of surfaces and shapes. right? So in general, it's a good practice to always keep a convention that whenever we speak of surfaces and the whatever volume is within them, surfaces will be denoted by outward unit normal. So we're going to convert that into outward unit normal. Okay, so this quantity I could rearrange so that my normal vector become minus. So I can add, I can multiply -1 inside, and inside and outside. So for surface 1, I could write minus f at 1 dotted with minus ex dA1. Yes. Surface 2 also I can do, but it's not consequential in this example. But let me do it nonetheless. And then so on and so forth. For 6th, where it really matters, you anyways have outward normal, so we don't need to change anything there. 6 dot yes, confused? Yeah. See, I cannot change the quantity, na. In the end, I should have my flux calculation same. I'm saying that, okay, we were all okay until here. When we write our flux, so if we, what we'll do is now, to answer this question, how much this quantity is f bringing in per unit time, we will add all of these. Flux, yahan se flux, wahan se flux, all the flux together. Now, that is fine, that is correct. But we have changed our convention. In some places, we have taken unit normal inside. We are just changing that. So we are rearranging term. We will not change. I mean, this sign. I mean, that total has to be plus because it's in. In has to be positive. So what I did is that I added minus minus here. I didn't want to add and then justify. I first justified and then I added these signs. Yes or no? So the reason to do this is so that in my mind. So let me. So when I write all 6, then I'm doing this. Everywhere it's outward normal. Yes or no? Please pay attention here. This will come to you anyways. Okay. When I write this sum physically, this is what it means, and everything is logical. Okay. I'm getting to something, so please be patient with me. Now, can I write this as sum? So how much in per unit time? So let me just do HMI per unit time. That answer to this question would be summation of. I don't want me to do summation. We'll do summation in the next step. How much in is minus F1 N1 dA1. Better to write it here. Just denoting. Doesn't matter if you write subscript, superscript. So I'm going to write this as my unit normal of the first surface. Can I do that? I'm just denoting stuff. Plus F2 again. Now I'll just follow a pattern. 2 dA2 plus so on and so forth plus F6 N6 dA6. I can write it in summation and put the minus sign outside. Fi Ni. This is not that Einstein notation I. Okay, these are different surfaces. Okay, this is a vector of ith surface. It's not Fi-Ni like that. Okay, and then dA whatever I. Yes or no? And I is going from 1 to 6. Now this, what I've written, is it general? Can you tell me if it's general for flux oriented in any direction? So in this example, I just took this direction, right? Now this formula of how much quantity in per unit time, will this be okay if I tilt the room a bit, keep the flux like that? Or to tilt the flux a bit so it's coming diagonally? So, so it will not be just 1 and 6 contributing, it will be 1 contributing a little bit, this surface also contributing a little bit, whatever is the dot product. Make sense? So it's general for any F orientation. It is general for any F as a function of R. I did not tell you what it was function of x square sine square x, sine square y, whatever function. So it's an arbitrary function. Okay. Now, is it valid for any geometry as of now? No, right? Because assume cube, it has 6 surfaces. If I want to write for any geometry, some of you might have done some numerical methods. How many of you have done numerical methods or at least heard of it? Okay, many of you. So you know that if you want to solve flux through this arbitrary quantity and put it in some COMSOL or some software, what will it do? It will make some meshes. It will divide this continuous surface into discrete surfaces. So can we write how much in for that software? So that would be I going from 1 to 6 or 1 to n. Yes, this is what your software will do. Okay. Now, if you are in again continuum approximation, if you have so many, I mean even more than a computation, more than a computational software, you're doing it on board. So we are now taking an abstract idea. We make infinitesimally small surface elements because we ultimately want to go to integral calculus. So this dA tending to 0, can I replace this with integral, right? That's what we do. So how much in is area f dot n dA? Now I remove these signs because my f, it is understood within this integral that f is a function of space over the area, n is a function of space over the area, and we are doing this integral over this area in the limit dA tending to 0. Yes? So if someone asks you, oh sorry, minus sign is, yeah, minus is there now. So if someone asks you how much quantity came into this material, any arbitrary material. Now this is valid for any shape, and it has this surface normal here, and surface normal, as I said, will keep changing over the space of area. Here it will be here. So wherever you go, it will point outward, right? For example, this bag is of arbitrary surface. Here it's pointing here. If I go down, it's pointing down. Yes? Okay. So now we will use this in today's class. With respect to outward normal. Yes. Yes.
At every point, we are only summing the contribution from the flux that is in the direction of the normal, against the direction of the normal.
This is cumulative of all the surface elements.
Yes, but
inside integrand, it is at each arbitrary surface element.
Yes, but at each arbitrary surface element, we are taking the dot product of the flux.
F and N, yes.
So that only sums the contribution from the flux that is pointing in the direction of the normal.
Yes. Yes. Just like
quantities transported, like shear or something for which
we will come to the shear part. Okay. So today we will take this idea for transport through a static quantity, because it has to be gradual, right? Okay, so this material is not moving yet. We'll make it move. Okay, so now just keep this in mind, and we will start mathematical modeling of transport processes. In this lecture, it will be static transport processes. I mean, transport processes through media which are static. So, a simple example would be a thin film of liquid through which you are studying concentration transport, or a thin slab through which you are studying heat transport. And you must have done some derivations. For example, what governs heat transport? What governs the temperature uh, map within the system? Let's say you heat it at 100 degrees, you cool it at 0 degrees, start the clock, and you will see the profile develop. What governs it? This temperature map? Some equation, right? Fourier's equation, or some people call heat equation. In case of mass transfer, you have a thin film or whatever film, and then this is diffusion. So you have a diffusion equation. Some people call it Fick's second law, but both of them are diffusion equations, very analogous. So for simplicity, we can just call them diffusion equation. One is diffusion of C and one is diffusion of T. Okay, so let's see how to get that mathematical model. Static or quiescent media. And before I start deriving, I will lay down 3 steps. It's a 3-step procedure. First is you decide what do you want to model. Heat transfer through this slab, you will have to conserve something. So let's say you want to find the idea of how the temperature map is evolving in time and space. Okay, what do you think that equation should obey? Because it has to be grounded in some fundamental principles that you have learned before. Yes or no? So for heat transfer, what fundamental principle that mathematical model should obey? There is energy coming and energy going. Any law that comes to mind that says energy cannot just disappear? First law of thermodynamics. So, and for mass transfer, you would have, so you have energy conservation, loosely speaking. Then you have mass conservation. In fluid mechanics, you have mass conservation along with momentum conservation, which is which basic law? Newton's second law, in which you balance forces. Okay. So the step number 1 is any transport process that you are considering should obey fundamental conservation principles. So depending on the transport process, you will decide, okay, let's balance, let's apply first law of thermodynamics to this system. That will be step 1. So basically decide the law that you'll apply. Decide the law. Step number 2. Once you have applied the law, and you have done in, out, all the balance you have done with respect to this, you will have to do this step that the area that you're taking, you have to make it, infinitesimally small. Why you have to make it infinitesimally small? Because see, ultimately we are interested in time, temperature map, concentration map. That gives us the point-wise information of T and C. Meaning, if I'm going to model this and do the first step here, I better get the equation that is valid at each point. It's of no use to me if it's valid for a bulk. So I need to take a small limit so that my heat equation or diffusion equation is valid at each point. Okay, so I'll take this limit. We will see it more clearly. And step number 3 would be using appropriate empirical laws. Why? Because we'll see after we apply this, it will not be sufficient to find the temperature map, because we will need the help of experimentalist, we will need the help of Fourier fix to supplement that model and to complete that model. Okay, so using the appropriate empirical laws, this could be also known as constitutive laws, which are nothing more than educated guesses. Why I say that? Because Fourier's law, as we saw in that limit, is not valid for all the materials. Fick's law is not valid for all the materials. Okay, you have multi-component mixture of exotic polymers. Fick's law you cannot apply. If you are looking at heat transfer through a slab at nanosecond time scale, meaning you give 100, you give 50, and you want to study, it's, let's say, very important for you to study what happens at very early times. You have to take that relaxation into account, so you cannot apply your usual Fourier's law. Okay, so that's why it is important to know these are not like fundamental laws, these are constitutive laws which are valid for a specific range of materials. Same goes for fluid mechanics, we'll see it. So whatever you're reading here is not just for heat and mass transfer, it's for electrostatics, electromagnetism, everything. And what we'll do today, you can take that quantity, we'll take a general quantity phi, it could be temperature, it could be concentration, it could be electrostatic potential, or whatever you want. So it's a very general derivation, and yeah, it's nothing but the constitutive laws are nothing but the educated guesses. Okay, so let's start. And okay, so consider, so let's say I'm going to study heat and mass transport through this bag. It's of arbitrary shape, and I'm going to look at just one lump. I have a thing to study, but I'm going to look at a collection of material points, and I'm going to apply my step number 1 to that collection of material points. Okay. So I have many infinitesimally small material points, and these material points constitute material volume. And by the way, velocity is 0. This is a static medium. This is under consideration, and although it's static, now I'm going to send a flux of heat or a flux of mass through it. F, and this F could be anything, but we have to choose what we are conserving. So let's decide. Let phi, which can be function of x, y, z, and t, be some per unit volume quantity that we'll consider. Okay, meaning every material point has this phi. Every point has this phi, and we're going to conserve it. How will we conserve it? Meaning we'll apply balance to it. See, you must have done this derivation not in this slide. This may look very foreign to you, but you might have done by taking a cube and saying, okay, the x pe aata hai, x plus delta x pe hai, in minus out is equal to accumulation, and if there is generation, we'll account for that. Yes, But then if someone changes the geometry, makes it cylindrical, what do? You redo the derivation. Someone makes it spherical, what do? You redo the derivation. Someone makes it toroidal, what do? So this derivation is arbitrary for any geometry, but we are doing the same thing. It's just that you will see some integrals. That's all. So what do we do there is the same thing we'll do here. Balance. So accumulation is equal to rate of in minus out plus generation. But we'll apply it at this volume in which phi is a function of space and time. So can you tell me, I mean, it's not, I mean, just think a bit, what will this accumulation term be? Accumulation of this phi. No. I mean, it could be anything. We are deriving an equation, right? So it could be a transient system. It could be a function of t. There could be an accumulation. So you have a flux, and that flux could be varying in time, varying in space. More flux coming in, less going out. Thing getting heated up. Thing or concentrating some moles. So it is non-zero. So I'm going to use dou because it's function of space and time. Dou by dou t of phi. Yes. But phi is a function of space, and phi is here. Did I, if I write like this, did I apply it on the volume? But I have to do the balance on the volume. So what should I do? Multiply by V. Okay. Okay, good. You could do that. But if phi is changing with V, then we can't do na. If phi is for same everywhere, we could do this. So what do? We do an integral with respect to V with respect to material volume. And then we have in minus out. Now, you remember what we did when the class started? What did we do? How much in? What was it? A or S, whatever. So that's the reason I did it before, so that you can continuously do it without jumps. Everyone is comfortable with this? Generation term? Some generation, some volumetric generation. Meaning, I mean, that lump that I've considered here, I mean, this entire bag, but in this in particular, could be generating heat, could be reacting and forming new moles. So I could also, and this is all volumetric. So I could do S, I think. Just to check. Rate of change of S. Volumetric. So this V is just to denote that it's volumetric quantity. Volumetric meaning it's happening at each point within that. It's happening everywhere. Okay. Now, can I do this? Can I take this inside this time derivative? Think about it. What does it mean to take the derivative inside the bracket physically? So this volume, we could only take it inside if this volume is not changing with time. In the current example that we have taken, volume is fixed, the static system. So we can take it. But do you think in fluid mechanics we could take it inside? No, right? So we'll come back to this. Something called Reynolds transport theorem. Okay, so we take this inside very easily. Is equal to minus n dot f ds. Remember the goal. What is the goal? These are the goals. We already did this. Now the goal is we have to make it infinitesimally small. I mean, I should have written dA and dV both. Now, either you could convert I mean, let me ask you this. Can you, okay, um, okay. If all the three terms that you have, one on the left, two on the right, if all of them were volume integrals, if all of them were volume integrals, if they were, then you could remove the integral sign. We could. Why? Because it's arbitrary. We can shrink the size of this volume. We can shrink the size of this volume. See, just like your conventional derivation from undergraduate, you took a thin element, you shrunk it, you made the element's area a bit smaller, dx tending to 0, you took the limit. Same way, I could say, in other words, that this volume that I've taken, since it's arbitrary, I could shrink it down to just one material point, just one point in space. So if I was in that privileged position, then I could have just said, this is valid for arbitrary volume, so it should be valid locally, should be valid point wise. Then our step 2 also would have been done. But this guy is sitting there with a surface integral. So what can we do? Can we convert this to volume integral? How? So what is it saying? What is this term? We already did some arbitrary volume, sorry, not spherical. You have some flux through this. Yes? Sum of all fluxes, doesn't matter, I can write bad English, right? So, sum of all fluxes through the surface is equal to sum of let me call this word expansion at each point in volume. I'm going to write something intuitive first, and then we'll see the mathematical form. Meaning, sum of all the fluxes through the surface. I had this small part which I was inspecting. My flux was coming in. It could vary in space or whatever, and I could say that whatever flux has come in versus out, it should be equal to whatever expansion has happened of that quantity within. So either I could track the activity of the flux, either I could track the activity of the flux on the surface, or I could track the activity of the flux at each point internally, not on the surface. Yes or no? They should be equal. No? So again, imagine you are not a cube now, you are this shaped room, and all of you are sitting here, all of your material points. Some flux is coming in from outside, raising your, and all of you contain this phi. All of you in your pocket have this phi. Huh? And some flux is coming and raising the value of that thing that you have in pocket. Now I could say I will account for whatever came in and whatever went out. And then that should be equal to, if I don't account for that, but if I account for each point, how much increase decrease happened in your pockets. Does it make sense? Same to hona hi chahiye. Otherwise, where else will it go? There's nothing in this room except you guys, right? So, isn't that Gauss-divergence theorem? That n dot f ds is equal to divergence of f dv. Why do I call this divergence? So now we already did a lecture, the online thing I uploaded. What is the physical meaning of divergence? How much is out? How much is it source of? So it's actually out minus in. Divergence का मतलब is out minus in. Yes or no? What was in minus out? Minus n dot f integral, right? We did this early on. So out minus in is this. Our intuition for divergence is out minus in. So everything is consistent. So we can convert this into volume integral. Okay. I'll remove this using Gauss-divergence theorem. Now I can say, okay, since we started with, or we considered arbitrary volume V, let's shrink it down to one material point. So I can just do this. Does this look somewhat like what you have always derived? Right? I mean, if not, it will soon look, because step number 2 is complete. This is your conservation equation for phi. So what is it saying? At each point, rate of accumulation of phi at each point now is the local divergence of flux at each point plus local source term or reaction or heat generation at each point. Now we have to supply F, this flux. Again, we have two candidates here which we will study, or which we are studying. So in case of heat transfer and then mass transfer. So now I'll make things more explicit. What phi could be? So in mass transfer easy, first let me write easy. So what did we write? Let phi be some per unit volume quantity. So in mass transfer it will be concentration. Is it per unit volume? Right? Units are mole per meter cube, right? SI units. What will be the flux? Yes? Mole per second meter square. Quantity by per unit area per unit time. And then your S would be simply reaction rate, volumetric reaction rate, and this will be mole per same unit. All of them should have same units. So mole per meter cube second. Yes. Now mass transfer we understood. What about heat transfer? Phi will be temperature? No, not temperature. Per unit quantity. Heat per unit volume. Some reference temperature. What's the unit? Joule per meter cube, right? Yeah. Because mCp delta T is joule, rho Cp delta T joule per meter. F is Q dot is equal to minus K del T. This is F, joule per meter square second, and S will be Egen dot. So now we can plug in for each case and find our diffusion equation for heat and mass. So simplifying, what you will get is the following. So you will have rho Cp here. Once you substitute rho Cp, you can take it to the other side. What is K by rho Cp? Alpha. So since there is a minus sign, you can do this as homework, so I'll do it quickly. This minus sign, that will become plus. So what do you have? So let me not be too quick about it. Okay. Yes. What is divergence of? We all did all this for what? All that practice for this only, right? Now we will assume for simplicity that K is constant and uniform. Constant, uniform are same thing? No, right? So here it's uniform, meaning it's same at all locations, but in exam it could be non-uniform also, right? K del square T plus Eg dot rho Cp dou T by dou T. The reference temperature is not a function of time, it's some reference temperature, so that vanishes. You can take this to the other side. K by rho Cp, this by rho Cp, this becomes alpha del square T Egen by rho Cp. This is your heat diffusion equation. You can do your mold or mass diffusion equation. What you will get is, again, something for homework, is very simple. Rho C by dou T is equal to T del square C plus some reaction term, some volumetric reaction term, but not some rho Cp वगैरह. There are some differences, huh? It's not the same. Okay, alpha and D, now that you see both are analogous to each other, they have same units. They should have same units. Meter square per second. You remember in one of the lectures I said that it's not K that decides your spread of temperature, or it's not alpha that decides your spread of heat. Alpha specifically decides your spread of temperature. That you see now clearly, right? So this alpha governs the rapidness of temperature spread and concentration spread. Okay. Now I want to give you all a question to think about, and we'll do it here only. Is that what if you remember there was a point here that I had volume integral, surface integral, volume integral. What if I did not convert that surface integral to volume integral and took my limit anyways? Then what would have happened? Of course, we will not get our governing equation, but could we obtain something else, something useful that we could use later? So we had this step, right? We took the time derivative inside. Some source term. So let's not apply Gauss divergence here. And let's say that we are shrinking the volume anyways. And I'm going to do it slightly differently now. So I'm going to assume that my volume has some length scale L. So imagine it to be cube, imagine it to be cylinder or whatever sphere, cuboid, with some characteristic, some length scale L. So volume would be of what order in L? L cube. So this is L cube. O means roughly of that order. This will be of square. This will be of cube. Now I'm going to shrink it. L tending to 0 or L much less than 1. I'm going to take L to be 1 microscopic value. 10 raised to the power minus 6. Which of these, so can you, so let's say if, as engineer, let me give you 10 raised to the power minus 6. What would this be? 10 raised to the power minus 18 meter cube, 10 raised to the power minus 12, 10 raised to the power minus 18 again. Now, what does this mean? Is that as you shrink down the size, this term will balance this term, and this term will have to independently vanish to 0 because there is nothing to balance it. So I'm talking in estimates point of view, that if I were to calculate this, let's say somehow computationally evaluate this will be a very small number, this will be a large number, or this will be a small number. Now, that won't be feasible because then the equation won't be balanced. You will have some large number equal to 0. Yes or no? So we reach a conundrum, we reach a problem, dilemma. So the solution to the dilemma is this guy balances this guy, these two balance, and this, as size shrinks to 0, independently vanishes. Meaning, for infinitesimally small volume, you have n dot f ds equal to 0. Physically, this will make sense now in a moment. I believe in the earlier classes, when I was introducing you to transport phenomena, continuum approximation to be exact, I told you that we are going to look at molecules but at a zoomed in level, a zoomed out level, and we are going to consider a box in which the fluctuations are not much. Yes or no? Meaning that box in which fluctuations are not much, it's in local equilibrium. Meaning, although you have this bag studying heat transfer, and if you go into that resolution of continuum scale, that small volume that you consider a bunch of particles or molecules together, they were in local equilibrium. Although your entire system is at a out of equilibrium phenomena. Why is it out of equilibrium? Because temperature is changing with space and time, and it will eventually equilibrate, go to some equilibrium. Heat and mass transfer and fluid transfer or momentum transfer, these are all out of equilibrium phenomena. But at the scale of material point, at the scale of continuum, that small cube in which there are molecules, it's in local equilibrium. When we point out and say this is T, temperature at this x, y, z, that temperature, that is in local equilibrium. It is itself not out of equilibrium. This is that. That if you shrink down the size so much, there is no flux into that small continuum volume. Does it make sense? There is large flux, but at the small flux, at the small level, there is no flux. So this is local equilibrium. Will this be helpful here? No. For heat and mass transfer. Will this be extremely helpful in momentum transfer? Yes. This will help us find the stress tensor. But I'm giving you a bit of foreshadowing, as we call it in movies. So keep this in mind, it will come later. So meaning surface integral of flux should independently vanish. Alright. Okay.
So, under this local equilibrium assumption, the surface integral varies as opens, but
yes.
But in non-equilibrium conditions, it could vary as anything else.
If you are in non-equilibrium at that scale, yes, then you are not even in continuum. Okay. Now another important note is that when I write this, what do I mean when I write this? When I write my constitutive laws, these are empirical laws coming from experiments. What do I mean? Aren't they instantaneous? Aren't they instantaneous? Meaning, as soon as you apply chemical gradient, what do you have? What do you have? That's what you're assuming, right? You apply temperature gradient, oh, flux. And how much time it took to obtain that flux? Zero. Absolutely zero. But in real systems, there is some small time associated with the application of, so there is a time lag between application of chemical gradient and temperature gradient and the flux being developed because of it. We do not consider here in this transport phenomena course, but you should understand that what are the approximations that we are making? We should know, right? So your typical Fourier's law and Fick's law, when you write this, these are instantaneous. At time t is equal to 0. But there is some sort of relaxation in the material. Why am I telling you all this? Because ultimately we'll do momentum transfer. Momentum transfer may, again, we will not deal with such systems because it goes in the regime of non-Newtonian fluid mechanics or polymer dynamics. But if you have a slurry sort of system made of polymers, polymers are these spring-like or elastic type material, viscoelastic materials. You apply gradient of velocity, just like concentration temperature, you apply gradient of velocity, the momentum transport will take time to develop. Okay, so if I were to write that sort of equation here for heat and mass, so that you could later relate to your fluid mechanics, it would be, I'll just make one addition here. Tau. So in your Fourier's law, I just added a time derivative term. Yes or no? This you are comfortable with, right? I see some lines on some foreheads. You are comfortable with this. I just added one term which tells that the material will take tau time depending on like what kind of material it is. If it is water-like material, this tau is very, very small. Practically, you can take it to 0. You can use your Newton's law of viscosity. If you're taking, let's say, in case of heat and mass transfer, if you're taking silver or diamond and so on, usual materials, this time actually is very low even for wood. So for us engineers in chemical engineering, it won't be useful. But if someone is doing high energy physics, or someone is doing is looking at very short times, if you give a thermal shock, what happens in that very small instant, then you have to take materials relaxation into account. So tau relaxation into that charging time. That charging time multiplied by unsteady effects. Does it make vague sense? This is not in the course, but you should know. Okay. We will end with boundary conditions. I'll write so that in the next class we can solve some problems. Are there any questions?
So can you just explain this one? NFDS 0 to जब हम इंटीग्रेट कर रहे हैं तो पूरे वॉल्यूम पे हो जाएगा वो तो जब हम
पूरे सरफेस पे हो रहा है वॉल्यूम सॉरी पूरे सरफेस पे इंटीग्रेट हो रहा है but that surface has shrunk down to a single point. So at that small point we shrunk the volume. You agree with that? You understood? Okay. So when we shrunk down the volume to a point, we found that these guys will balance independently. This guy will have to be 0, otherwise we are saying something is equal, some 2 is equal to 0 something.
our convenient we make this equal.
No, not for our convenience, for it to make sense, for this equation to make sense, because you have bunch of volume integrals and this is surface integral. So you are okay with this? You are okay if I give it value 10 to the power minus 6 and then I write down rough magnitudes? So you know that this will never be equal to this here. So this cannot exist. So this cannot be like, an equation cannot be like this, that something 10 to the power minus 18 is equal to this position. So meaning this has to be 0, actually 0. Meaning we are at something fundamental here, at a small point, at a local point, there must be equilibrium. Okay. So within that small cube or small volume that you took when you were making continuum approximation, there is no build up. there is no delta T in that volume. That's what we are saying. So that point has T, that point has C, that point has V, that point has rho. And here, that point doesn't have any net flux. So, okay, let me draw this. I drew this volume there, na? And I said it's made of many material point. Let me zoom in here. When I'm doing that L tending to 0, I'm actually looking at here. Let's zoom in. This is my point. I'm saying, and this is my flux F. Here N dot F is equal to 0. Here, surface of this. That's what I'm saying. Okay. So one can use principle of local equilibrium to derive boundary conditions, and that's what I did last semester or last time I took TP. This time I didn't do because it's just some additional derivation which is not very useful. I did this derivation because later it becomes useful. But so if you want to see the derivation of boundary conditions, you can look at Dean. I will give you the page number for that. It's in chapter 2 of Dean. Dean is one of the reference books. Okay. So I'm going to write these boundary conditions for 1 dimensions, and you can easily extend it to 2D, 3D. And I'll write for heat and mass transfer as usual. So this is a condition for local thermal equilibrium, meaning that if you have an interface, let's say this is your slab, this is the outer boundary, and let's say it's cooling off using some convection. I'm assuming you know at least a little bit of heat transfer. Okay, you must have solved these problems. You use some boundary condition here, right? What we'll say is that if this is not there, you have another slab at this point. This is phase 1, phase 2. T1 is equal to T2. Okay. Sometimes we don't need interfaces. We say something like this one. Dirichlet boundary condition, meaning a value is specified on the surface. So Dirichlet means a value of temperature is specified. Okay. Interfacial flux balance, meaning again you have an interface at some location x equals to xi. This is L, this is 0. What will you write? Fluxes are equal phase 1 and phase 2, meaning x equals to xi equals to xi. Meaning that there is no build up. Whatever is flux is here should be the flux leaving. So this is an ideal contact. That's what must be given to you. So these are some basic interfacial conditions. Another type of this, if I can write, is this. You must have seen it n number of times. What are these dashed lines? Insulation. So what is the flux? Flux is 0, right? So Q dot is 0, meaning dou T by dou X is, so Q dot at X equals to 0. At X equal to 0 is 0. So temperature profiles always make some sort of 90-degree angle here. Another kind is the convective flux. Again, as I said before, you have some slab heating to the ambient. Let's say there is some internal heat generation and it's heating out. What do you usually apply at these boundaries at x equal to 0, x equal to L? You have a slab, internal heat generation, open to ambient. What do you apply here? Again, assuming you know some basic heat mass transfer. Conduction equals to convection, right? So you write that minus K dou T by dou X at whatever the position here, let's you want to write, is equal to H T minus T infinity. But there's a catch here. This is usually, when I teach to UG heat transfer, they make this mistake. They apply this condition here also and here as well. But you have to flip it. So a good way to remember this is that it's H into T lower coordinate minus higher coordinate. Because your X is in this direction. Na? So always take it like this. Lower minus higher coordinate. Because when we study Newton's law of cooling even in 12th, we say na this plate is cooling. So we write HA delta T. So it's at lower coordinate minus the higher coordinate. So this would be HA T lower coordinate minus T higher. In x direction it would be tilted. Okay. This is of which type? When a flux is specified, flux is specified. What type is this? Neumann. What type is here? Also the flux is specified, right? We are saying this flux is equal to, the conductive flux is equal to convective flux. Specified. So is it Neumann? Think about it. It's not really true. Flux is not specified. Flux is given as some function of temperature, right? So this is known as mixed. This is also a common mistake. One of the common mistakes from undergraduate students. They classify this as Neumann. They say, okay, dt by dx is equal to something, but that's not a value, right? That t there is also a variable. Again, this is at whatever coordinate you want, x equal to 0 or x equal to L. Okay. I'm doing a quick job of it because, I mean, I'll share the notes with you, but this is something that you must have done. So it's a recap only. In case of mass transfer, now let me write them quickly. If you have any interface, so let's say you have a liquid film, this is phase 1 and phase 2, can you write down C, whatever we wrote here, C at like phase 1, x equal to xi is equal to C, or phase 2, x equal to xi? Can you do this? For mass transfer, can you just replace T with C and be done with it? Sorry. Or something known as equilibrium partition coefficient is needed, because different phases can have different solubility of the material. For example, you may have concentration in it, and this phase may not like it at all. So concentration cannot be equal. Yes. So it is subject to some K. Partition coefficient. For gas liquid interface, it comes from Henry's law, I think. For liquid it is dependent on what is the relative solubility in each phase. Okay. Point number 2, again, interfacial. Oh, sorry, that one. Conditions. For example, if you could have phase number 1, you could have some reaction happening on the surface. You could have a liquid film. We'll see some examples in the next class. You could have a liquid film with a reaction happening on the edge of this film. Then what would you write? Diffusive flux is equal to J at x equals to L is equal to some reaction. So reactive flux, right? Some reaction we'll write. Depending, I am not writing what reaction because depending on order of reaction, 0th order, 1st order, 2nd order. So diffusive flux equal to some reaction. I could make again, since I made two types of these interfacial boundary conditions, I could again make a Neumann type boundary condition, meaning this is my liquid film, one side is solid. Diffusion in solids is very, very low. So it's like almost inert surface. So similarly, you will have dou C by dou T is equal to, dou C by dou X is equal to 0. So you could have a Neumann variant of that, or you could have this variant. So let me write. So 2.1 is fine, I'm not going to write it. 2.2, let me write. You have a film in which there is some concentration C, and it could give away this concentration outside. It could diffuse outside. So just like we had, what did we have here? Conductive flux is equal to convective flux. Same way, diffusive flux is equal to convective flux. So you have minus d dou C by dou X at X equals to L, if this is L, is equal to K. K is what? Mass transfer coefficient. Units for H is watt per meter square Kelvin. Units for this is meter per second. C minus C infinity. Very similar. Okay. One final condition and then we are off. Is for both heat and mass transfer. So let me use pen. It's known as axisymmetry. Have you heard of it? Meaning, if you have a axisymmetric heat transfer, this water bottle which I asked but I didn't drink, if there is uniform heat generation, let's say this is cylinder, and there is uniform heat generation within it, what is the condition that I will use and the periphery, if it's open to ambient, I will use this, right? Conductive flux is equal to convective flux. At x equal to 0, what will I use? There is uniform heat generation. So what will I use? Dou T by dou R should be 0, right? This is the axisymmetric condition. You can use principle of local flux equilibrium. You can see the Dean's book. If you want to know, you can approach me. I'll send you the notes to prove axisymmetry. Right now, it just comes as a dogma ना कि यही होता है, सदियों से यही हो रहा तो यही करना है, right? But you can prove it also. So axisymmetry dou T by dou R 0, meaning for cylinder. If you have a sphere, again, dou T by dou R equal to 0. If you have a slab, and if it's heating both sides, and if it's heating uniformly and leaving the heat flux outside through convection at x equal to 0 or at the center plane, you will have dou T by dou X equal to 0, right? So you could have dou T by dou R or dou T by dou X equal to 0 for problems like this, for symmetric problems. So that would be called as symmetry. For cylindrical, it will be known as axisymmetry. Okay. Basically meaning Q dot is 0, J dot is 0, flux is 0. Okay, with that we'll stop. In the next lecture, we will study the nature of the heat equation. What does it say? What does this guy say? Yeah.